Good day, Dr. Muhammad Iqman Ishaq. Today I'll be presenting my project for MMK 21103, Computer Aided Engineering titled Static Structural Analysis of a Wall-Mounted PC Monitor Support Arm. Let me briefly introduce myself. My name is Kartik Ganesan. My matric number is 241311022. I'm from Mechanical Engineering Technology Machining. My program code is UR6521002. Firstly, we look at the background of this project. Wall-mounted PC monitor support arms are commonly used in offices, control rooms, and industrial environments to save space and improve ergonomics. These support arms are subjected to static loading due to the monitor weight and behave like a cantilever beam, where one end is fixed to the wall and the other end is free. Poor design may cause high stress and excessive deformation, especially near the wall mounting region, which can affect structural safety and performance. Therefore, computer-aided engineering is used to analyze the structural behavior and identify possible design improvements before manufacturing. Next, I will briefly explain the objective of this project. The first objective is to analyze the equivalent 1 minus stress, total deformation, and factor of safety of the wall-mounted PC monitor support arm under static loading conditions. The second objective is to evaluate the structural behavior of the support arm and identify the critical regions where high stress and deformation occur. The final objective is to propose and compare design improvements and to assess their effectiveness by comparing the analysis results with the original design. Continuously, we see the scope of this project. The study is limited to structural analysis only, and all components are assumed to be made of structural steel. 3 design configurations are analyzed, which include the original design and 2 improved designs. A fixed support is applied at the wall mounting plate, and the bonded contacts are defined between all interacting components to simulate fully tightened fasteners. A 300 Newton downward load is applied at the VESA mounting plate, and the same boundary conditions and loading conditions are applied consistently for all 3 designs to ensure a fair comparison. This slide shows the flow chart of the methods used in this project. First, all components of the PC monitor support arm were modeled and assembled using CATIA. The complete assembly was imported into NC's workbench for analysis. Structure steel material properties were assigned to all components. Bonded contact conditions were defined between interacting parts to represent fully tightened fasteners. Next, boundary conditions and loading were applied, where the wall mounting plate was fixed and a 300 Newton downward load was applied at the VESA mounting plate. For mesh generation, a 3 mm tetrahedral mesh was used. This mesh size was selected as a balance between accuracy and computational efficiency, and tetrahedral elements were suitable due to the complex geometry of this assembly. After analyzing the base design, the same mesh settings, material properties, boundary conditions, and loading conditions were applied to the improved designs. This ensures that any change in stress, deformation, or factor of safety is solely due to the design modification, allowing a fair comparison between all designs. Finally, the static structural analysis was solved, and the results were post-processed to evaluate 1 minus stress, total deformation, and factor of safety. Let's proceed with design configurations. This slide shows 3 design configurations analyzed in this project. Design O is the original configuration, which uses a flat support arm with standard component thickness. Design 1 is the first improved design, where the support arm modified into U-shaped cross-section. Design 2 is the second improved design, where the thickness of critical components increased. We see all the 3 designs one by one. The image on the slide shows the CAD model of original design. Design O is the original configuration, which uses a flat arm with standard component thickness. This design is used as the baseline for comparison. Design 1 is the first improved design, where the support arm is modified into a U-shaped cross-section. This modification is intended to improve stiffness by changing the geometry without significantly increase the material usage. Design 2 is the second improved design, where the thickness of critical components including the support arm, wall plate, and VESA plate is increased. This design aims to further reduce stress and deformation by increasing overall structural stiffness. All three designs were analyzed under the same material properties, boundary conditions, and loading conditions to ensure a fair and meaningful comparison. Let's go into the boundary conditions and loading applied in the analysis. The images shows the location of boundary conditions and loading. A fixed support was applied at the wall mounting plate to represent rigid attachment of the monitor support arm to the wall. All contacts between components were defined as bonded contacts, which simulate fully tightened fasteners and prevent relative motion between parts. A 300 Newton downward load was applied at the VESA mounting plate, representing the weight of the monitor acting on the support arm. The load was applied in the negative y direction, and the same boundary condition and loading were consistently applied to all three designs to ensure a fair comparison of results. This slide presents the overall results obtained from the static structural analysis. Three main response parameters were analyzed, which are equivalent 1 meter stress, total deformation, and factor of safety. For the original design O, the maximum equivalent stress obtained was approximately 68.86 megapascal with a maximum total deformation of 0.586 mm and a minimum factor of safety of 3.56. After the first design modification, design 1, the maximum stress was reduced to around 45 megapascal, while the total deformation decreased to 0.407 mm. The factor of safety also increased to approximately 5.56. For design 2, which includes increased thickness at critical components, the maximum stress further reduced to about 42.21 megapascal and the total deformation reduced significantly to 0.296 mm. The minimum factor of safety increased to approximately 5.92. From these results, it is clear that both design modifications improved the structural performance, with design 2 showing the best overall performance in terms of lower stress, lower deformation, and higher factor of safety. Now we jump into the discussion part. This slide discusses the observation from the analysis results. For all three designs, the maximum stress is concentrated near the wall mounting plate, which is expected because the support arm behaves like a cantilever beam, where the bending moment is the highest at the fixed support. The maximum deformation occurs at the VESA mounting plate, which is the free end of the structure. When comparing the designs quantitatively, design 1 shows a reduction in maximum stress of approximately 36% compared to the original design, where the stress decreases from about 68.96 megapascal to 45 megapascal. For design 2, the stress reduction is even higher at approximately 40%, with the stress reduced to about 42.21 megapascal. In terms of deformation, design 1 reduces deformation by about 31%, while design 2 achieves a reduction of nearly 50% compared to the original design. These results clearly show that the proposed design modifications significantly improve the structural performance of the monitor support arm. Continuously, we see the structural phenomenon involved in this analysis. The wall-mounted PC monitor support arm behaves like a cantilever beam, where one end is fixed to the wall and the load is applied at the free end. Under this condition, the bending moment increases towards the fixed support, which explains why the higher stress is consistently observed near the wall plate region for all designs. The applied bending moment also causes bending deformation, with the maximum deflection occurring at the free end, which is the VESA mounting plate. Therefore, the stress and deformation patterns observed in the results are consistent with fundamental beam theory and cantilever behavior. This slide explains the scientific reason behind the improvement in results. In this study, the material remains the same for all designs, which is structural steel. Therefore, the changes in stress and deformation are mainly due to geometric modification, not material properties. In design 1, the flat support arm is changed to a U-shaped cross-section. This modification increases the second moment of area, which improves bending stiffness and reduces both stress and deformation. In design 2, the thickness of critical components is increased. Increasing thickness further enhances stiffness and reduces stress concentration by distributing the load over a large cross-sectional area. As a result, Both design modifications improve structural performance, with design 2 showing the most significant improvement. In conclusion, a static structural analysis of wall-mounted PC monitor support arm was successfully conducted using NCs. 3 design configurations were analyzed under the same material properties, boundary conditions, and the loading conditions. The results show the proposed design improvements effectively reduce stress and deformation while increasing the factor of safety. Among the 3 designs, Design 2, which involved increasing the thickness of critical components, demonstrate the best overall structural performance. Therefore, the objective of this project was successfully achieved. For future work, further improvement can be carried out through structural optimization to reduce weight while maintaining strength. In addition, fatigue analysis or dynamic analysis can be performed to evaluate long-term performance under cyclic or time-varying loads. Alternative materials such as aluminum alloys can also be investigated for lightweight application. Thank you.